This animation is truly wonderful. We have here the two views simultaneously and synchronously. So here we have our observer. I've put him in the vicinity of Athens, Greece. We see the celestial sphere, inside it the Earth, with an observer position located upon it, and as time goes by, the Earth will rotate inside the celestial sphere. Here, simultaneously, is the local view of the observer. We see his horizon, his northern horizon over here, and this is the half of the sky that the observer will see. And as we begin our animation, I've also drawn a few star patterns on the celestial sphere. We see here the Big Dipper near the North Pole, Orion near the equator, and near the southern celestial pole, the Southern Cross. And as our animation begins, note that if the observer looks to the east, Orion is just rising above his eastern horizon, as it was exactly in our animation, in our simulation, and now Orion will rise high in the sky, cross his meridian, and set in the west, and this will happen as the celestial sphere rotates about the observer, or as the Earth rotates, and we see Orion rising and setting. On the other hand, if we look at the motion of the Big Dipper, we notice that as the Big Dipper moves, or as the Earth rotates, the Big Dipper's circle around the pole essentially never carries it below the horizon. It performs circular motion around the pole, and it never ever sets, and so that makes the Big Dipper part of what we call the circumpolar star. There's a whole region around the pole for each observer of stars that, as the celestial sphere rotates or as the Earth rotates, never set below the horizon. And correspondingly, if you look at the Southern Cross, you see that our observer in Athens will never be able to see it. It will never actually rise above his horizon. So there's a similar region around the opposite pole that never rises. And so these stars are never visible, these stars are always visible, and then the stars in between rise in the east and set in the west. And it is this relation of the two systems of coordinates that we need to understand. Repeating, as the sky rotates above the visible celestial pole, stars close to whatever pole you can see never set, stars near the opposite pole never rise, and stars in between, or near the equator, rise in the east, move west across the sky, set in the west. Of course, for example, if you're at the North Pole, then you have half of the sky that is circumpolar and never sets, half that never rises, and stars can't rise in the east, and therefore at the North Pole, their trajectories are just horizontal circles parallel to the horizon. And we see this in these collection of beautiful images. The two images on the left are star trails. In other words, somebody left the shutter open around the south celestial pole on the left and the north celestial pole on the right. So the stars in this image would have been moving counterclockwise, and the stars in this image would have been moving clockwise. And then on the left, we see a beautiful image of star trails near the horizon. This is Orion rising, and you can see from the fact that Orion is rising and moving to the left, you should be able to figure out that this means this image was taken in the southern hemisphere. And indeed, if you're a northern hemisphere denizen like me and you look at Orion, he seems to be doing a headstand. This is because in the southern hemisphere, one's head is pointing in a different direction in space. And so we have the beginnings of an understanding of what it is that we see at any given place. And we're almost ready to make the calculation. And so the thing that we need is this description of the zenith. So I already described to you that our zenith at any point is a point on the celestial sphere whose declination is equal to our latitude. Now, over the course of a 24-hour rotation of the celestial sphere, which point along that celestial parallel we see changes. You see all of the stars over a 24-hour period which have that declination pass overhead. And so what we're going to do is, at any given instant, we can look which celestial meridian contains our zenith. And we can look at the right ascension of the celestial meridian and call that our local sidereal time. And this will, of course, change with time as the celestial sphere rotates to the east or to the west, or the Earth rotates to the east. Either way, your sidereal time will increase by about an hour each hour, and a complete rotation of the Earth, or equivalently of the celestial sphere, will advance your sidereal time by 24 hours. So, sidereal time is the name of the celestial meridian which coincides with the local meridian, the one that includes our zenith. And of course, over 24 sidereal hours, when this right ascension advances by 24 hours, this is one full rotation of the Earth. So we can use the stars to measure time. The motion of the stars across the sky is a way to measure time, and indeed, in one sidereal hour, the celestial sphere shifts by 1 hour of right ascension, one parallel giving way to the parallel moved by another hour, and until the 20th century, this was in fact the definition of our units of time. A second was defined in terms of the rate at which the Earth rotates. This is a pretty stately and fixed rate, and it's no coincidence that until the 19th century, this was the most precise way to measure time that we had at our disposal. Thing to note, of course, is that different locations on Earth will measure different sidereal times, because depending on your longitude, you will see overhead different celestial meridians, and as you move to the east, you will see later and later sidereal time, because moving to the east, you see stars overhead that are farther and farther to the east along the celestial sphere, and so 15 degrees of longitude east advances your sidereal time by an hour, but this varies continuously, so that moving east by 20 meters changes your sidereal time by some small amount. Returning to our view of Athens, we can now read off the sidereal time in our picture. Remember, the sidereal time is the time indicated by the celestial meridian that coincides with our local meridian, and we've seen that before. This is the 1 hour meridian, so the sidereal time in Athens at 9 p.m. on November 27th was 1 a.m., and of course, as we allow time to progress by an hour, sidereal time will progress. We can see that by allowing time to progress, and an hour later, it is 10:01, the sidereal time has changed, it's now 2 hours sidereal time. Now, we can use this, now that we understand the position of our zenith and the location of our local meridian, we can use this to find a particular star. So let's suppose that at 9 p.m., we wanted to find a particular star. Let's imagine that we wanted to find in the sky this particular star, Alpheratz, in the constellation Pegasus. So if you look, Alpheratz, you can look it up, has celestial coordinates. It has a declination of about 30 degrees and a right ascension of about 0 hours. It lies at the intersection of this line of declination and the prime celestial meridian. That means that Alpheratz will rise in our east, become as high overhead as it's going to get when it's on our local meridian, and then start setting in the west. So the best time to view Alpheratz, in fact, is when it is directly overhead. Because it is on the prime celestial meridian, best time to have viewed Alpheratz would have been at 0 hours, at sidereal midnight, which means at 9 p.m. we're an hour too late. But that's okay. We can fix this. We can just, through the wonders of technology, go and observe Alpheratz at 8 p.m. Here we can move time backwards. And indeed, as advertised, at 8 p.m., Alpheratz is right on our celestial meridian. It has risen as high as it's going to rise and has not yet begun to set. So at that time, 8 p.m., or more importantly, midnight sidereal time, Alpheratz will be on our local meridian. Where will it be along the local meridian? Well, this is where Alpheratz's declination comes into play. Alpheratz is at a declination of 30 degrees. Our zenith, we said, because we are in Athens, is always at a declination of about 37 degrees. This means that the angle, the zenith angle of Alpheratz, the distance between Alpheratz and our zenith at its meridian crossing at the time when Alpheratz is as high in the sky as it gets, well, its zenith angle is given by our latitude minus its declination, in general, the absolute value of this, which in our case is about 38 minus 30, or 8 degrees. So Alpheratz will attain a minimal zenith angle of 8 degrees, or a maximal altitude of 82 degrees above the horizon, quite high. Now, this tells us almost where it is. This defines it to within a circle, but because it's on our local meridian, it can only be either north or south of the zenith, and because the declination of Alpheratz is less than our latitude, our zenith is at 38 degrees, Alpheratz only at 30 degrees of declination, its azimuth will be 180. It'll be due south of our zenith at the time that it is as high as it can get. And so if we observe Alpheratz at sidereal midnight, we know exactly where to find it. And now if we need to observe Alpheratz later or earlier, we simply use the fact that we understand that over time, the sky rotates about the celestial pole at the rate of 15 degrees an hour, so that if we wait an hour, and we indeed are observing at 9 p.m., Alpheratz will have moved 15 degrees to the next celestial meridian, and indeed, that is what we will observe. So we have a way of finding the approximate position of a star over the course of the night. Notice that there is an explicit formula that gives you altitude and azimuth as a function of sidereal time and declination and right ascension. The formula involves trigonometry, so we won't apply it. What I want us to understand is the principle from which it's derived. So, we've achieved what we wanted. We did not complete the mathematics because it would involve trigonometry, but I think we have the idea. We know, given the sidereal time and our latitude, how to figure out where in the sky the pole is, which line of right ascension is directly overhead, and then moving east or west, we count an hour per 15 degrees, and we can find where the rest of the sky is. So we have an understanding of which part of the sky will be visible to us at any given time at a given position on Earth. We've essentially solved the problem. The one missing ingredient is that we still need to figure out what this sidereal time thing is, because our watches do not measure sidereal time. It was 1 a.m. sidereal in Athens when it was 9 p.m. on November 27th. If we could get the translation right, we'd be set. So that's the next thing we have to take on.